The conclusion of Doppler effect is that if source moves at a v of s and observer move at v of o, that will result, well, obviously that vs is with respect to the ground and v of o also is with respect to ground. That will result a change of frequency received by the observer that can be described as new frequency equals the original frequency of the numerator is v plus minus v of o associated with observer move, and denominator is v minus plus with vs associated with the source move. This is a very interesting result for Doppler effect. Let's try to use this equation to solve a couple of problems so we can have a better understanding of this equation. Now, first sample problem is from your homework. It is on page 538 of problem 40. It says a block with a speaker bolted to it as it connects to the spring, having spring constant, and so on and so forth. Okay, so let's take a look at it. Now, if we have a frictionless ground, and this is the wall, and that is a spring constant K. Say, for example, we have a block also frictionless, and we have a speaker, let's say, mounted on the top. That's a speaker. Now, the total mass of speaker plus the block is given. And we have several conditions that it's given as the total mass of the speaker and the block is 5 kilogram, and the amplitude of unit motion is 0.5 meter, which means if this is the equilibrium position, the furthest that it can move is half meters away, and it also will move to the left if another half meters away. This is the so-called amplitude of simple harmonic motion. And also we know that the frequency of the speaker is 440 hertz. The frequency of the speaker is 440 hertz. And for that, room temperature speed of sound equals 343 of meter per second, and so on and so forth. Now the question is, question A, if the speaker emits sound waves of frequency 440 hertz, determine the highest and lowest frequency heard by the person to the right of the speaker. Now if there's a person standing right here, for example, and what is the highest and lowest frequency heard by this person? Now obviously that this is source. When source moves to the right, and observer will receive a high frequency. When source moves to the left, and observer will receive a low frequency. As we learn from simple harmonic motion, that at equilibrium position, speed reached the maximum. So at that time, we only have kinetic energy 1/2 m of v. This is maximum. This total energy comes from the initial 1/2 k of amplitude squared. So we can solve this maximum speed at equilibrium position. If we want that one, that is obviously k over m square root times a. So in our case, if k is given 20 Newton per meter, m is 5 kilo square root, and amplitude is half meter, so the result is 1. This is actually 4, square root is 2, so that's 1.0 meter per second. That's the maximum speed. So if we learn about Doppler effect, in this case, source moves, observer doesn't move. So we have this f prime equals to original frequency 440 hertz, and since source does not move, since observer doesn't move, that v of o equals 0, so we only have v on the top, that is 343, that's speed of sound, and this is also speed of sound, and we have a minus plus choice of, that is speed of the source, in this case is the 1.0 for the max. So obviously if we choose plus, we get a frequency lower than 440. and in this case, the lowest, let's say minimum, is very close to 439 of hertz. If you do the calculation, the max, if you choose this minus 1.0, it will get 441 hertz. So when does that happen? When the block speaker is at equilibrium position, moving at the maximum speed towards the observer. Observer receive 441 hertz at the highest frequency that observer will receive. And when this combination moves to the left, which is away from the observer, the minimum frequency the observer receives is 439 hertz. We're talking about frequency. Now the next question, the question B, is if the maximum sound level heard by the person is 60 decibel when he is closest to the speaker. Well, obviously, if we take a look at it again, we have this. If this is the equilibrium position, and then the amplitude is half meter, so that is the block. Since the person is here, so this is the closest position. If that the closest distance between the source and the observer is 1 meter, and then the furthest distance, since this is the equilibrium position, and the block, which the furthest position it can reach is another amplitude to the left. So the furthest distance will be 1 meter, because this is 1 meter. This is 1 meter. Plus twice of amplitude A. The question is, when the source is 1 meter away from this person, sound level at R equals to 1.0 meter is 60 decibel. The question is, what is the sound level when the source is at the furthest distance? That is obviously 2 meters away, because the amplitude is half meter, twice it will be another 1 meter. So the question is, what is the sound level? Well, we can approach this problem in an easy way or a little bit more complicated way. And I simply suggest we approach it with the easy way. We're going to find the difference. And then we know, since we know the sound level for this one is 60 decibel, if we know the difference, and then we just subtract, because when the source is further away and you get lower sound level. Okay, so we use the higher sound level, subtract the lower sound level, as we know that is 10 of log of the first position, which is closer, subtract the second position, which is further. As we know, log A minus B is log A divided by B. That is time the reciprocal. So we have this 10 of log of times the reciprocal will give us I1 over I2. And we also learned that the ratio of intensity for a point source will result at the ratio of the distance square. In that case, R2 is 2 meter, R1, so the ratio is 2, and 2 squared is 4. So we have 10 log of 4. So once we know that, we can find the new sound level is actually 60 decibel, subtract 10 log of 4. We just need to do just some little calculation, and the result is still in decibel. What if both source and observer moves? Let's look at the situation. Case A, if we have source move to the right and observer move to the left. This is all with respect to the ground. Case B, if we have that source move to the left and observer moves to the right. Well, we pretty much know, because this source and observer move towards each other, and it will double the Doppler result. So we observer will receive a high frequency for sure, and this moving apart will receive a much lower frequency, that's for sure. But what about such a case? Source moved to the right, observer also moved to the right. So it really depends on who moved faster. What about this? Source moved to the left, observer also moved to the left. Okay, so let's take a look at what do we do. New frequency f of prime associated with original frequency with this speed of sound plus minus speed observer, speed sound minus plus speed of source. Now how do we use this equation? Okay, case number A. New frequency equals to original frequency. When we consider the numerator, that is the observer, observer moves. When we think observer moves, we do not think about the source. We assume, we know the source is here. We assume it doesn't move. Now the observer moves towards the source, we suppose receive higher frequency, so we choose plus for VO because higher frequency need to do plus for the numerator. Okay. Now when we come down to the denominator, that is about source. When we think about source, then we do not think about observer. We think that observer is at rest. Sources move towards the observer, so observer must receive a high frequency. A high frequency, the denominator must choose a minus. That is how we choose. Now just remember, you have to decide, because of this motion, will the observer receive higher frequency or lower frequency? Then you decide to choose plus or minus for denominator. Okay, so that is this. Now let's practice again. For the situation of case number B, that the numerator is about observer. So when we think about observer, we assume source is at rest. Now the observer is moving, since source is on the left, observer is moving to the right, is away from the source. So you receive a lower frequency. Lower frequency means you choose minus for denominator, numerator. Okay, when we consider about the denominator, that is about source. So we assume observer does not move, source is moving away, so we receive a lower frequency. Denominator, lower frequency, you must choose plus. That is that. Case C. Numerator is about observer. When you think about observer, you assume source does not move. Observer moves away, you choose minus because it receives lower frequency. Now, for denominator, it's about source. When you think about source, observer does not move. Now, the source is moved towards the observer, so it receives higher frequency. Higher frequency, you must choose minus for denominator. So you can imagine for the last case, if you're smart enough, it will be plus plus. Why? Okay. The numerator is about observer. Observer, source. Observer move towards the source, receive a higher frequency. Denominator is about source. When you think about source, observer does not move. So source now is moving away from the observer. You receive a lower frequency. For denominator, lower frequency means plus. See? That's how you judge. A couple of things I want to point out, that all the speed of sound is with respect to the ground. Speed of observer, speed of source, both, we should say all of them, all the speed of sound, speed of observer, speed of source, are with respect to the ground. They must have the same reference